Here with another lesson for you guys. Today we're going to cover common trigonometric identities. We did this a little bit last year in pre-calc, remember, with some of the more in-depth identities. You're always going to have that reference, so it was really about knowing how to use them. So we did a little bit of a gallery walk about it last year. But I figured it would be a good idea to just quickly review it, review some trigonometry so that you guys can see it a little bit more and hopefully get a little more comfortable with it. So we're just going to start off with the basics again, a quick review. Can never review this stuff enough. There's a lot going on at the same time. So trigonometry is the study of right triangles, or if we have a triangle, it's got a 90-degree angle in it. If this is true, then we can apply trigonometry. So we need to have that right angle so we can have a hypotenuse, an opposite side, and an adjacent side. So if we're looking at our angle, our trig functions are relating all three of these sides. There's 3 different sides, which means there's a total of 6 combinations of comparing these sides. So if we look out to the opposite side length from our angle, we can just label that opposite. One thing I do want to mention too, this symbol right here is again called theta, and that refers to an angle. Greek symbols, we got to get used to them. Again, just reviewing so we can get more comfortable. So we have the opposite side. A lot of people aren't sure which one would be the adjacent side or which one would be the hypotenuse. So one good thing to notice is that the hypotenuse is always opposite of the right angle. So we have our hypotenuse right here. And then finally, all that's left is our adjacent. Notice how our adjacent side is right next to our angle. So if we have our adjacent side, our opposite side, and our hypotenuse, then we can actually talk about these in terms of some really well-known, or what should be some pretty familiar values now, or functions. So we know SO, CA, TOA really helps us out in this case, which claims that the sine is going to be the ratio of our opposite side and our hypotenuse. Our cosine of our angle is going to be the adjacent side over the hypotenuse. And finally, we have the tangent of an angle, which relates the opposite side to the adjacent side. So we've kind of really been focusing on these, and in fact I'm just going to rewrite them out so you can have them. So the sine of our angle is equal to the opposite side. I'm just going to abbreviate it as O over our hypotenuse. So if you have the opposite, you have the hypotenuse, you can use your trig function in order to find the ratio between the two. You have your cosine of your angle, which is going to be the adjacent side over your hypotenuse. And finally, you have the tangent of the angle, which is equal to the opposite side over the adjacent. I'm not going to spend any time reviewing an example of this. If you're still unsure about how to use these, how to put in values, please come see me. This is something that you're going to see over and over throughout the year. It's going to pop up in calculus at seemingly kind of random places, so it's really important to have a good conceptual understanding of what trigonometric functions do and how they relate to this right triangle by comparing that angle to the ratio of some sides. Okay, so the angle compared to a specific ratio. So I'm going to go ahead and just leave this right here for a second so that, and make sure it's nice and focused so that y'all can have these theorems. So go ahead and pause it if you need a second to write it. But I'm going to start reviewing these. So we have our sine, cosine, and our tangent. And so It turns out we also have three functions called the secant, the cosecant, and the cotangent. And so those are talking about the other three combinations we can have for these. So we can have opposite over hypotenuse, but what if we want the hypotenuse on the numerator and the opposite on the denominator? Well, in that case, we can divide this whole thing by 1 divided by sine theta, and you'll get what's called cosecant. 1 over cosine of theta is going to give us our secant, and 1 over tangent of theta is going to give us our cotangent. So one thing to notice here too is that you can also talk about your tangent in terms of sine and cosine. So tan is going to be sine divided by cosine. And since cotangent is 1 divided by tangent, it's just the reciprocal of this fraction. So cosine of theta divided by sine theta. We had a few more that we kind of dived into last year with the gallery walk. We have our Pythagorean identities. Sine squared of theta plus cosine squared of theta is equal to 1. We can derive that from our right triangle as well as our unit circle. If we divide everything here by cosine squared of theta, we'll get this line. And then if we divide everything right here by sine squared of theta, we're going to get this third Pythagorean identity. Next up, we have some lesser known ones. These two are going to be the big ones that you're going to need to know, these two groups. This one might pop up. It comes up in proofs sometimes. If you have two angles added or together, one subtracted from the other inside of a sine, you can actually expand it out like this. And same with cosine. You can actually expand it out your single cosine function into about 4 cosine and sine functions. Double angle is just saying if you have twice the angle and you want to show it as maybe half of it, you can expand it sine of 2a to 2 sine of a cosine of a. You can also expand out cosine of 2a. And so this one has 3 different representations. This one's kind of the most used one. But if you actually put in your Pythagorean theorem, Pythagorean trig identity into either of these, that's how you get these values right here. So this one was subbing in sine squared of a for 1 minus cosine. And then this one right here was from substituting in the cosine squared of a with 1 minus the sine squared of a. Okay, so that's how these ones come up. Gonna do 2 examples, and then we'll be good to go. So let's start off with a more straightforward example. And this is really just gonna be learning how to simplify these things. So maybe we have something like the tan squared of theta divided by, let's say, the secant cubed of theta. And we want to simplify this to one identity. Simplify the expression. So, yeah, let's just simplify the expression. So, right here, it doesn't seem like there's much going on. But if we refer back to our trig identities, we'll notice that we have some values that will actually be helpful. We know that the tangent is in terms of sine and cosine, and we know that secant is just 1 over cosine. So if we're checking these out right here, well, we might want to write down the identities. And the big thing we want to do here is get everything in terms of sines and cosines. If we can do that, then we know what cancels out. So we have that tangent squared of theta is just the tangent of our angle squared. Okay, so just a notation thing. And we know that tan squared of theta is just going to be the sine of our angle theta divided by the cosine of our angle theta. And this whole thing is squared. So if we wanted to show it in a good notation, we would put that square value back with each individual one. So I just distributed the square to each. So we know our tan squared theta is just sine squared of theta divided by cosine squared of theta. Our secant cube of theta cubed. Well, we know from our identities in the back, the reciprocal identities, that this is just going to be 1 over cosine of theta, and then this is all cubed. So we could also show this as just 1 over cosine cubed theta. All right, so going back to our original equation, we know that this can also be shown more explicitly as tan squared of theta divided by the secant cubed of theta. So if we wanted to show it in terms of our two functions, well, this is going to be sine squared of theta divided by the cosine squared of theta divided by 1 over the cosine cubed of theta. So in this case, in order to do this property, we need to take the reciprocal of the second. So we have sine squared of theta over cosine squared of theta, and then times cosine cubed of theta over 1. So just like we can cancel out common factors in cubes and squares, we know that we can cancel out our cosine squared theta, and we'll have 1 cosine left. Cosine times cosine times cosine divided by cosine times cosine. We're just going to have a single cosine left. And from here, it's just multiplying all the way across. So this reduces down to 1, 1. So we have a denominator of 1. We don't need that. But we have sine squared of theta left times cosine theta. So this is as simple as we can get this thing, which is why you might see it shown as this. But notice how we have less terms. Right here we have tan, tan, secant, 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 and we were able to drop it down to sines and cosines. One more example I want to do is a little bit more difficult one using our Pythagorean theorem, or Pythagorean identities. So we want to verify in this next example that tangent squared of x plus 1 times the cosine squared of x minus 1 is equal to the negative of the tangent squared of x. So just quickly right here, notice how I switched out the theta with the x. Because they're just placeholders, it doesn't matter what variable we use. I also dropped the parentheses, which is okay to do as long as there's only one term in the argument, okay? So you might see it look like this. It's not implying anything else, because remember, this is the input of our function. It's not saying to multiply s and I and n squared by an angle. It is a function in itself. You put in a value, and there's a bunch of rules that you follow inside of here in your calculator, and it spits out an output. So going back to here, we're going to need two identities here. Our first one is going to be a Pythagorean. Actually, both of them are going to be Pythagorean identities. So we're going to first need to take this thing, figure out how exactly we can turn this into a single trig term. So if we look back at our previous notes, you'll find that 1 plus tan squared of x is actually equal to the secant squared of x. So we can actually turn this thing into the secant squared of x. Our next identity, we're actually going to need to do 2 steps in order to do this. So this one has a cosine squared and a 1. That's a good hint that I'm going to need to use my sine squared of x plus cosine squared of x equal to 1 Pythagorean identity. So I want this to be over here, which means this is going to go over here. So I need to subtract 1 off of each side, and I need to subtract a sine squared of theta, or of x in this case, off of both sides. So minus 1 minus sine squared of x. These two will cancel. I'm going to switch these around, but we get that the cosine squared of x minus 1 is going to be equal to negative sine squared of x. So notice how we had to kind of rearrange that, which means that this guy right here is going to be the negative of sine squared of x. Well, just from last the last example, we found out that the secant of an angle is just 1 over the cosine of that angle. So we've got 1 over cosine squared of x times negative sine squared of x. So the next thing we need to do is just simplify this out. So we get negative sine squared of x over cosine squared of x. Or we get the negative of sine of x over cosine of x squared. Well, we know that this is going to just be our tangent. So this finally evaluates down to the negative of tangent of x squared. Or, looking up here, we have verified that this is equal to the negative tan squared of x. Check. So a lot of good notation reminders right here, lots of good reminders of what each identity does and how we can kind of use them to simplify these trig expressions. Again, you might not see more than these simple reciprocal ones, maybe a Pythagorean every once in a while. These are really just good to know that they exist, but really make sure that you understand how these three work and how they relate to the secant, the cosecant, and the cotangent, as well as this tangent.